guys. I'm doing this speech. And next speech is goes from it's my great honor to invite Professor Osawa. It is now surveying on Fusion University, and today will give us some engineers topic which is related to the medical and the rehabilitations about robotics. So let's give a big clap to welcome him.
So thank you for the kind introduction from Professor John. So I much appreciate this committee member and the society staff. So today I talk about the next generation mechanical design and manufacturing technology for the medical application. So my department is the mechanical engineering and hardware engineer. So I'm a professor in the KEISUKE University. I'm just starting the introduction. So I was born in the Aichi. Aichi means Toyota, the center of Japan. So after that, I entered the Kansai University. So I do snow area. So I'm interested in the airplane or the space engineering. So but I changed the mind. So I don't remember. So but I'm curious in the medical robots. So especially surgical robots. And so started with the KEISUKE University. So this KEISUKE University is a collaborator with the medical doctor or some precious at that time. So after graduation, so this is the Waseda University in the Fukuoka, KEISUKE area. So this is the assistant professor, the supervisor, the teacher supervisor, also the supervisor from Dr. Chuan. So this is 2 years. After that, I'm academic PhD in 3 is half year, and currently assistant professor in the KEISUKE University. So my hobby is basic graph drawing. So I'm also played in high school students, but now it's only watching. So Taiwan is one of the strongest baseball country. So I also I'm very respected Taiwan play. And the drinking, so I attended the Oktoberfest in the beginning in this year. So I'm drinking 1 liter beer. So I'm enjoying the drinking something. And so my research interest is medical robotics and soft robotics and mechanical elements. So then my research society is IEEE science and Python. Python means mechanism and machine theory. So it's a European society. So this is the main society. So 2 years ago, I visited Aichi for the first time. So he is a professor at the National Symphony University of James, and this is the team. So this is the Taiwan Instrument Research Institute. So I'm very precious time for high level of research and very passionate researcher. I'm very precious time. So I'm the introduction to KEISUKE University, so my university. So this is a campus. This is the core campus. This is the main campus, Eco campus. This is the engineering some part of the research main campus. And the hospital campus, and the KEISUKE campus, and the OAS campus. So this is the collaborative with each other. So maybe this is a big campus. And so this is introduced to Fukuoka. Fukuoka is here, and Taipei is here. So only 3 hours the flight. So very close. So if you have the chance, visit the Fukuoka or some Tokyo or Osaka. So very close. So please please yes. So this is my research topic is mechanical elements. So what do you see is the mechanical elements? So this is the main part is the screw or the shaft, gear and arm. So the spring bearing, so belt and chain and joint rings. So my research is focused on the gear. So especially this kind of the traditional type of gear is already exists, but maybe the application so that for the medical application. So it's important. additionally, so in recent years, digital fabrication is important. For example, the 3D printer, the paper cutter, the laser cutter, CNC machine. So this kind of technology is advanced in recent years. So especially my research focus on the 3D printer. So this technology is very exciting and the high potential of the future manufacturing. So and introduce the medical robots. So medical robotics shows mainly the four types of devices. Yes, this is the surgical robot, pharmacy robot, and service robot, care robot. This is the main topic. So and the market is increasing now. In the future, maybe more increasing the market and expanding. So I'm focusing on the two topics. So one is the robot-assisted surgery. So this is the famous of the surgical robot, Davin surgical system. So this is the minimal invasive surgery with possible to the cavity. So and there is minimal damage. And this is confirmed effectiveness, the Samja. So another reason, the robot-assisted rehabilitation. So like the exoskeleton. So for example, the famous is the HAL, or the Velvo, the Velva, some technology. So this kind of applies medical applications. So this kind of effectiveness already confirmed and shows an improvement is expected. So currently I am focused on the new technology for medical, for reform of mechanical engineering. So for example, so compound mechanism is much more, and variability, so variability and brightness, and the safety for the human. This kind of the viewpoint is important. So one key technology is component mechanism. Component mechanism means the friction mechanism that achieve the force and motion transmission, so through the elastic body deformation. So this is for example, like the gas. So this kind of the technology is interesting. An example of the medical device using different kinds. For example, the forceps and the hand and the assisted robots, so assisted and navigation device and stereoscopic microscope. This component mechanism can create the smaller and lighter medical robots and the devices. So this is, for example, so my first impression of the component mechanism. So this is a very interesting, so the four elastic hinge exists. So this is the elastic deformation. So this is a combination, so can make the new transmission method. So this is the very interesting mechanism. So this is introduced some technology for the other reasons. For example, this is the elastic, so this is the clip, and this is the architecture, some hand robot, and this is the metamaterial, that's something using the component mechanism. So this is the forceps and headphone, this is the toy, and this is the generated animal motion. So this kind of interesting research exists, but this is the one of the big program. So this kind of hinge is easy to grow. So it is necessary to optimize the design parameter. So it is one of the big goals. So I introduced the objectives of my research. So main subject is for divided space. First is prevention, and then next is diagnosis. Next is the therapy, the last is rehabilitation. This kind of space is the important technology. So we aim to provide next generation mechanical design and manufacturing technology for medical application. This is my goal. So first is prevention. So some people the currently program is aging. So this is causes the muscle atrophy, the cardiovascular disease, some metabolic disease. So this is called death, so physical reduction. So especially so stroke is very dangerous. if the support devices, it's a smooth like walking available. So this is Professor Chuan's research. So this is a combined emotion recognition. So from the brain wave and the heartbeat. So using the AI technology. So this is the 3D map. So the emotion and the fatigue. So this is the, for example, so the during the walking. So walkers watching the as on myself the emotion. So this is the it is the fast the walking speed. So it is the more comfortable so region. So this is my research direction. So after feedback the speed. So this is the totally assisted road system. So this is the introduced research methodology. The EEG sensor is a portable type EEG sensor, heartbeat sensor. This is a very powerful type. And so this is news. So news is detected, can detect the heartbeat. And so this is the 2D model, and this is the 3D model. So it is, can be seen in the photos. So this is the final version of the assisted robot. So currently, so using the 3D printer technology, so this is the finalized prototype. This is using the third motor, pressure sensor, and printer, and some combined with the electrical circuit. So this is the totally it is 1.2 kilograms. This is the very lightweight. So and controlled by the smartphone. So by tuning the automatic assist or the manual assist. So this is the final checking the usability. So people can comfortably walking assist. So this technology is a smooth walking assist and easy to attach. So this is the different task. So this is the total acquisition process. The first is the microcontroller. So after the walking, so is the pressure sensor value is changing. This is the microcontroller is actually after that as a calculate the next walking cycle. Finally, so they prevent the overload by the limiter, and this is the walking cycle estimation process final version. And so this is how to estimate the walking cycle. So we propose the five methods to estimate the target walking cycle. So one is the initial stance phase and average calculation and linear regression, non-linear regression, and the combination of 3 and 4. So finally, I check with this effectiveness of during the walking. So it is most effective the 5, so combination of the 3 and 4. This is the linear regression that was after 3 strides, so speed as 3 strides cycle. This is the linear regression and non-linear regression. So it is a very important point. But this is the so difficult to precise estimate. So this is the combination of the important things. And the focus on the how to promote the walking. So for the elderly, so to maintain the difficult, so the motivation. So it is using the MR goal. So this goal is shown on this slide. So this is the walking cycle is can be seen. So users can promote the motivation. And so this is the mechanical assist devices. So we focus on the anchor assist. So this is the mechanical cost is very reduced from the motor electricity. So this is the smooth walking assist. And so this is a haptic device, so the walking assist device. So using the vibration speaker. So it indicates the time, walking cycle time. So using this is a pressure sensor and vibration speaker, so it indicates the timing and how to timing the ride. So it is a haptic device. And final one is so this is the muscle. This is a walking assisted robot using the exoskeleton, and additionally, so I am supported to go up and go down to the ladder, and starting up and sitting down the assist automatically. So detecting the user posture. And so additionally, we developed a new type of joint. So this is the center of the hip joint is very difficult to point. So this is the center of the point is different point. So this is the image for the human joint, human hip joint. So next topic is the assist tools. So this is using the EPR. This is already commercialized assist tools. So using the rubber bed. So this is a mechanical assist tools. So not using the motor. So additionally, this is the assist the standing one. So this is for example, this is the rubber bed is the 3 position. So this is the same time as the elbow and the shoulder and the knee joint and the assist. So it is very lightweight and low cost is important. Next is the mechanical assist. This is the additional mechanical, so remote center motion using. So this is the hydraulic peak, not the 3.1 kilogram. So it is assisted for gas spring. So this is the gas spring. So using. So this is the easy to understand. So it is the center motion is the shoulder response. So it is assisted the very smoothly. And so assisted some workers motion. For example, so the wiping, some doing, some grind, so carrying some life cycle, life motion is assisted. So next topic is diagnosis. And research about the chronoscope. Do you know chronoscope? So it can be detected for colorectal cancer. So it is a self-interpreted from the animals. So it is very interesting. So this is the doctor educates how to interact with the endoscope. So what is the difficult point? So this is the when they use the endoscope, they push it from the outside body. So that this is only stretching from the advanced. So what the expanded, if you have the attached the self-propelled device, it is no pushing and the smoothly advancing what is the chrome board. So there is some technology using the mechanical engineering. So it is a pneumatic system. Is automatically, so there is a changing the direction and smoothly inversion. So but this system is pneumatic system is a little bulky, so for the compressor. It is the work point is different implementation point. And so this is the rubber spiral bed. So and this is the floral type. It is very interesting. So the March floral type is using set program. Now this is like the inch one. So this is using the pneumatic and some kind of biomimetic sure. So this is a release and stretching. So this is a property. And finally, the spiral telescope this is a spiral rubber tube outside of the endoscope. It is achieved the insertion. So first prototype is from inspired by the sea. Do you know the drilling sea? So this is the end to drill for the port, like the bonnet. So and the first prototype is this one. So very small, so about 20 millimeter, using the friction shaft and the motor. So key technology is the warm air mechanism. So warm air mechanism, so this is the warm and coil. So this kind of technology applies in some kind of the industrial area. And I'm first prototype this one. So using the prototype. So this is self-propelling using the square gear. So this is interesting. And this is adjust to the column wall size. So using the conical gear. So this is the sliding the conical surface, and this is changing the diameter. And the final version is using the springs. So this is elastic spring. So this is changing the diameter. So but this kind of gear is damaged to the column. So it is one big problem. So the next I come up with idea from sensitive robot. So I create the toy. So to consider this sensitive robot. So this is very interesting. So please remember this text. So and this is already this is a sensitive robot. This is only actuating. So this is a soft ground. It can be self-propelled. So this is I come up with the idea. So this is same as the sensitive robot base. So I'm using the puzzle like the canoe or the sun inspired by the biomechanics. So this is the rubber tube, and this is the chronoscopy training model. So the self-propelled. So mainly so I'm using the warm gear. So this is the motor outside the body. So this is transmitted from the friction shaft. So this is the warm gear rotation. It is very simple fiber mechanism. So this is the photo database. So this is the capacity introduction. So this is the capacity delivery. So please enjoy this time. 今回はサウスエリアです。 the one of the famous outside restaurant is ramen noodle with some delicious food. This is one of the mozzabe is the soup with the vegetables. Thank you very much. So maybe take everyone that is so we can take a seat. The next topic is therapy. Therapy means surgery or some cure the disease. So what do you think the future surgery? So maybe so in recent years some AI technologies, deep learning, some ChatGPT. So maybe in the future we combine this kind of technologies for the surgery. So I've come up with an idea. So this is conventional approaches. This is the surgical system. So this is remotely actuated by the remote controller. So this is the surgical structure. So this is not intuitive. So the ultimate intuitive is this is inserted from the arm, so from the abdomen up. So I'm using the VR technology. So this is the final goal idea. This is only the 25 the total cavity. So the diameter is very thin. So I'm using the 3D camera and support hand and one hand. This is the intuitive surgery. So this is the first prototype. So this is about 11 millimeter. Under the 5 fingers hand. So totally is 15 motor actuation by the wire driving mechanism. So it is a smoothly actuated, so detecting the hand motion. And my part is the control method and simulation system. So this kind of the control parameter is tuned. So this is a demonstration, very interesting. So this is the diameter is 11, so let's see. So this is used in manufacturing the milling. So engineering plastic. This is the check with the pair speed test. So the some item the plastic. And the finally so the check with the insert. This is the trocar. Trocar means the core. So like this. So this is the result. This is the important point. So finally, so we implemented the VR and this is the final version of the assistive robot. Obviously, understand so the intuitive control and so the head posture is detected and actuated by the maximum is the variable. And so finally, so grasping the objects. So, but the currently the vibration is around the problem. So using sub motor, and in the future replace with the GU motor, something the maximum motor or some precise control motor. This is the better choice. So next topic is the component mechanism forceps. So this is one of the big programs, the gastrointestinal cancer. Gastrointestinal cancer means so some part of the father and the liver, stomach, some large intestine, small intestine. Some cancer is one of the big programs. So especially lungs, the prostate and the stomach occupied with the high ratio of the cancer. So, but the early detection is important. So it can be minimal invasive treatment. So EMR and DSD. So this is the minimal invasive surgery support gastric cancer. So doctor is using the tool. So the surface of the gastric cancer. So cutting the cancer. So this is the difficult point is the not of the dot and the narrow area of this point. So this is a too big problem. So I propose the how to grasp the mucosal membrane. So this kind of cancer. So using the electronic knife, so using cutting the mucosal membrane. So this is the proposed system. So this is summarize several types of joints. So maybe mechanism is an important point in this slide. So like the sliding, the rolling, the sliding, and the bending. So some technologies exist. So my point is this is the bending. So this is the good point for the easy to actuate and the no vibration and no lack of play. So this is the important point. So as the other technologies applies other regions. So the surgical growth is this complex mechanism together. So I've come up with this idea as one part of the forceps. One part means only one part. This is the glass part and bending part in one part. So this is using the 3D printer technology. This is finalized. Using this is wire driving. So this is actuated with 2 dots bending and 1 grasping. So 1 grasping, this is for grasping the needle. This can be seen for actuation. So this is the total system's overview. So I'm part of the grasping and bending part, transmission part, and the driving segment. So this is the normal, so only using the mechanical transmission system. So this is the good point is low cost. So only this one part is very useful for the future implementation. So this is the over the prototype. So using this is grasper and this is a handle. Some process is 2.5 millimeter base. So it is one proposal. This is the actuation demonstration. So using the contact mechanism, so grasping and bending, this is and it is inserted from the conventional endoscope. This is the important point. And intuitive control is important. And so I check in the bending angle. So this is 90 degrees can be bending. And the grasping is a little small. Maximum is 0.6. In the future, now with the multi-material technology, it is more bigger grasping force is better. And driving using the wire path is visible, and each wire path is different, changing the friction. So this is the modeling of the friction and force with the relationship. So this is the if the wire path is changed, so this is the increasing the force. It is the modeling is a belt friction theory. We have belt friction theory. And so the modeling. So there is some technology for modeling, so elastic model. So I'm using the pseudo body mechanism. So this is summarized some technology. This is finite element analysis is model is more useful, but the computational cost is high. But the accuracy is some point in the basis. And the coastal model means elastic model, and the cubic model is the same. So this is high accuracy, and the computational cost is below. So my proposal is supervision model. This is low computational cost and the middle accuracy. It is a good point for the balance. So this is finally checking the process and here the proposal as well as the model comparing. So here is difficult to model the prediction. So we're using the proposal model. So average error rate is very reduced, and so this is a precise model. So what is the stress evolution? So again, so it is benefit and advantage and disadvantage. And finally, we are checking the using modeling. So this is the near column. So the cutting is the electric iron. So this is the proposal for the system. So the last thing and the electric measure. This is one of the possibilities successfully. So the next is I introduced Switzerland. And last year, so I'm staying in Switzerland 83. So very precious time in the life. So I visited some European countries, so Germany or Italy or France. If you have the time, so maybe enjoy the European countries, some food or some precious place. So I stayed in the rehabilitation engineering laboratory. So this laboratory is three topics: so explorer, assess, and restore. Especially the combining the new technology, some physiological signal, combining some biofield. And assessing using the haptic device, some motorized device. And the restore is attached the handle to skeleton using the spring mechanism. So I'm research about this the handle skeleton bodies. That's the known application. So I introduced already application is the rehabilitation technology. So this is the simplified mechanism and we are creating the flow motor by the variable time. And the skeleton is using the springs, 3-layer springs. So it is a simplified mechanism. So this is the pediatric type is very interesting design. Some graphing is acid. And this is the stroke patient, the rehabilitation. So I briefly introduced my pediatric. So finally, rehabilitation is the last topic. This is my product is already exists for the commercial devices. So this device is ergo motion. So like this one. So this is already same motion as it. But this is a little dangerous because if you user move the arm, it is protect from the micro arm. So it is dangerous form. So we propose so neutral limit for the error level. So this is the limited requirement for comma lightweight space safety. So the purpose is develop a small and lightweight for limiter that improves the safety and durability of the variables. So I propose the soft gears. So using this is a symmetric is a form 3 plus a program printer. So this is elastic material, especially APA. So using this material, so this is can be deformed easily. So it is one of the safety designs. So I've come up with idea, so new productivity using this course here. So this is by using of here, the teeth deform and slip. So the overload, so blocking the rotation. So it is a complementary power transmission mechanism integrated, so achieving smaller and brighter mechanism. So this is using the FEA, so checking the flexibility, so it can be rotated, and this is the analysis cut-off power. So this is the demonstration movie. So normally this is can be machine the soft gear and digital gear. So but if the overload by this is the screen, this is the second thing. So this is the splitting the teeth and rotation is called. So it is a very interesting behavior. So this is obviously understand. So the slow hyperscale camera is the motion. This is sweep the motion. It is the elastic deformation interesting points. So in the future, maybe replaces the other material in some other parameter is better. So I'm using the cantilever model. So if I use I can model easy to calculate the code. So this is like a simple cantilever that can be deformed by the digit gears. So reverse slip is myself itself the deform. So this is the model is the difference. So this is the area. So using the model. So this is the rotation, but this is the stop. So this is the slipping the teeth. And this is the reverse impulse. So this is the moving. So this is the stop. So this is the deform the elastic weight, and so this is the slip. So this is the final version, currently final version. It can be actuated with very low, so it can be stopped. So by the lock is so it's actually small. It can be seen the slip and stop with the actuation by very low. So another more topic is the rehabilitation, the rehabilitation system. Very important. This rehabilitation system. So maybe so you can know the COVID-19 is can go to the hospital. It's difficult to go to the rehabilitation. So difficult. In service center, the limited number of the patients and therapists. So the resource shortage and can go frequently and high cost. So we developed the remote rehabilitation system using the virtual rehabilitation center. Using the remote area can be seen by laptop. So using the motion capture system, so detecting the joint angle. So this is the first trial. So using the robot actuated, so remote area. So and this is the other area. So actuated, and this is the remote actuation system, and can calculate the long lateral motion angle is calculation. This is rehabilitation is important for the lateral motion. So this is calculated automatically. So this is one of the good point. But this is using the motion capture as a high cost. So next is I propose using AI open codes. So this is the open codes used for the detect the time warranty system. So this is the alignment versus the match. So it is the calculate the similarity errors. So and this is one of the good point. And in the future maybe it can be available in the rehabilitation center and home for the center. And I propose using the media light. Media light is detecting some human motion using the low computational cost. So this is open source in the Google by Google. So this is can be useful for the automatically calculate the joint angle. And so this is calculate the real angle. So this is I'm checking the accuracy. So this is the total research introduction. So my methodology is combine some technology. For example, also the biomechatronics is the center portion. So that, for example, mechatronics, some biotechnology. So this combines important point. So in the future, medical robot is this thinking is important. So maybe the future one, so the collaborate with each other is more high level of research achieved. I'm thinking. And so finally I introduced my laboratory. So because in this year I changed the laboratory direction. So my laboratory is precision manufacturing laboratory. So this is different from the medical lab. So my laboratory research about the gear manufacturing and CMP for the semiconductor. So this is the two topics is the main topic. So and changing your direction or the same direction and wondering the point. So that if you have the chance, please collaborate with gear technology or some medical technology and some CMP technology. Thank you very much. So this is the laboratory. Two Dr. Post students and Master Post 10 students. And 3 professors, including me. So if you have a chance, please contact with this email address. Thank you very much.
Switch the softness of the material in your lab.
Yes.
So why would you make this decision?
Thank you very much. Nice question. So the one direction is the soft gear, my main topic. So this is the mechanical element is the one is the topic. So maybe soft gear is interesting. So what the digital gear is important for the industrial design. So maybe both is the
What is your vision going forward for this research? What would you like for the future to look like that you contribute to?
Thank you very much. So wondering the direction. So what's my main interest in the soft robot and the medical robot. So maybe this technology is applied to the medical robot because this is a fundamental mechanical element is improved. Is medical robot technology is advanced. So maybe the combined is important. Maybe this is fundamental. So not interested in research. So what's important for the industry? So the combined is important.
So what is your call to action, or how can all of us help? how can all of us help enable what you're doing? What is your kind of call to action to the field?
This is future direction.
No, like, what would you like all of the rest of us to do that would help and contribute to your goals?
In the future.
Other people can give you some help, how to collaborate.
Yes. Maybe so. I'm research about the manufacturing and design. This is maybe main topic is this discussion. So maybe it can be collaborated with my knowledge is medical law and fundamental mechanical engineering technology. Combined, it can be available, maybe especially in clinical research. Yeah.
Anything else? Okay, so I have some questions. Because I saw a lot of slide that is in my PhD stages that a lot of graphics made by me. So I'm really, that's a lot of memory for me because we have some strong collaborators with Osawa. I have a question about your robotic skill. And you have shown small robotics with some small features. I have a question about how to keep the stability, how to prevent the vibrations when you control that kind of robot.
Thank you. So it is an important point. So because some devices are initialized, so some problem is the cause. So because big robot is actually easy. So but small robot is actuation is a small motion. For example, so the so this is the wire mechanism. So it is actuated from by the wire. So but this is precise actuating is difficult from the motor. So but for the checking the rarely, so I'm tuning the parameter, control parameter. So maybe it is possible to use ultimate precise control. So and the vibration is about the big program. So it is depend on the actuation motor. So maybe the select and the good motor is important.
And another question is, in your researches, and many researches will embed to the human. So how to select the material of your robot? How to select the material?
Material, select material. Thank you very much. So, but this is the engineering philosophy. Maybe it is important point is biocompatibility. This is important aspect. So some engineering philosophy is biocompatibility, okay? But some 3D printer material is difficult for using this kind of robot. So maybe in the future, 3D printer materials expand the biocompatible material. So maybe it can be seen in the future to make a robot.
So, anything else? I think that is enough to close this section. Let's give a big clap. All the topic and is finished. Please enjoy your lunch. Thank you.
reach.
Made by Japan.
Yes.
So from Japanese company.
So, this it is biodegradable, very quickly in salt water, and you can 3D print it pretty easily. And it has properties similar to metal.
How about strengths?
14 megapascals, which is not bad. And it is flexible. And if you put it in salt water, it dissolves in just a few days. It specifically is good for ocean, like marine applications, for packaging and things like that. It's completely food safe, so you can use it in medical devices. You can use it in food packaging. They're trying to replace PLA. Because PLA degrades very quickly. It's a good thing to make toys out of, but not manufacturing products.
But from Americans, we should use a Japanese partner. Japanese. Kind of.
Well, we have 2 papers where we worked on characterizing both the mechanical and fracture properties of this material. They're under review right now. So hopefully, so we already have a whole data set with hundreds of data points. We're characterizing this material. As soon as the papers are out, we share the data set will be. But the data set we include with the papers. So we submitted the paper to the International Journal of Polymer Science and then to CD Instruction Paper from CD. So hopefully those 2 papers will be accepted and then the data set will be and Canada approved the data set to be published. So it's new data that they didn't have. We were able to successfully print it and injection mold and compare the difference. This material actually, one of the research findings that we found is the difference in properties between injection molding and 3D printing is only 5 to 15%. For ABS is 60%. So it consolidates really well when you 3D print. And you don't need any special equipment to do it. If you're printing different PLA, you can print this material.
So what about cost?
Well, they provide the material.
Oh. Exactly.
You can buy PHBH commercially, and I think it's about $100 a kilogram. This is not bad.
No. Wow.
So that would be 3 times the price of my one. But it's biodegradable. It'll get better over time. But it's made from vegetable oil. I'm getting no idea.
So maybe you can Google it and check that.
No, we got some unmarked rolls of material from the company, and they said characterize it, let's see what happens. They're like, we took some data, here's our data, see if it compares. Our data was way worse than their data, so we're thinking maybe ours is more realistic. We did 5 replications on every experiment, full factorial DOE. We went through compared with injection molding and printing. We got a huge data set.
Are the results consistent?
Very consistent. Less than 1% standard deviation.
Very good result.
No, the material does warp very quickly when you heat it, and it degrades quickly if you heat it too much. So you have to be careful with that. But we found that actually bed epoxy doesn't work very well with this material because it's oily. It doesn't stick. But if you use painter's tape, you know the tape they put in the corners of rooms to paint, it actually works very well.
All our temperature degrees.
So we did it from 190 C to 230 C.
I think that's pretty enough for human.
Oh, yeah.
So that's pretty good.
So the human should be
How?
50,
Yeah.
around 50, 55 C.
I think that's really good. Yeah. Pretty good research.
Yeah. So Kaneka, the Japanese company, they make this material. So maybe reach out to them and see if they can work with you too. Because a lot of times they're happy to have people work with their material. They just provide the material for free, and they just say, just partner with us. Let us know what results you find.
Okay. So that is real from Japan or that's a company in America?
So it's a Japanese company we're working with. Kaneka has an office in Houston.
Oh, okay.
And so we work with the office in Houston. Yes,
Ah,
the main company is in Japan. They make it in Japan. It's not made in the United States.
have you been to Japan before?
No,
Oh, really?
I need to.
You can invite him to keep us on top.
Absolutely. No, my area is in mechanical design. I just saw in design and manufacturing, so. Now, here in Texas, let me know we can come to our university. Are you coming to UTC? It's going to be in Houston next year. The Engineering Design Conference, ASME.
Ah, yes, IGDC.
Yes. So I'm on the 10th committee for UTC.
Oh, really?
So I'll see you there. And Texas A&M is a 1.5 hour drive from where the conference will be. So you should come visit and see our labs.
Are you attending this year's SAT? No?
It's been in California? This year. Yes. So it'll be in Houston? Yes, I'll be there.
Okay.
We're working with
Is that the end of August?
I think that it started making the second week of August, because the third week of August is when all the classes start.
Yes.
And so every fall semester, we always miss the first week of classes to go to this conference.
You organize this conference?
So I'm on the design for manufacturing and lifecycle engineering sub-conference. So I was the conference chair last year, and I'll be the secretary, the technical committee secretary this year. I've been working with this conference since I was a graduate student, so. I've been to every single conference since 2018. I found that one way to get involved with some of these professional society conferences is once you have your PhD and you're appointed as an assistant professor, just email the organizers and say, how can I help? Because they say, oh, you're willing to work for no pay? We'll give you a title.